So welcome to plenary lecture of 2022 KPS Spring Meeting by Professor David J. Wineland, hosted jointly by the Korean Physical Society, KPS, and the Korea Institute for Advanced Study, KIAS. I'm a professor and vice president of Korea Institute for Advanced Study. I myself am working on quantum information science at the KIAS. It is a great honor for me to introduce Professor David J. Wineland. He shared the Nobel Physics Prize in the year 2012 with Professor Arosh. Nobel Committee cited that they manipulated single quantum systems and measured. And that was the beginning of realization of quantum computation. And Professor Wineland was working for National Institute of Standards and Technology, the NIST, and working on atomic clocks. And as soon as he heard about the idea that atoms could be used not only for clocks, but also for quantum computers, he started to work on quantum computation. And now he is a Philip H. Knight Distinguished Research Chair of University of Oregon. And he's going to talk to us on individual atoms as clocks and bits. And we are going to have 50-minute session. After that, we are going to have a question and answer session for about 10 minutes. And you can send me the question by chatting, or you can raise your hand virtually. Let's welcome Professor Wineland, please.
Yeah. Okay, all right, thank you. Let's see, so, well, anyway, you can see the title of my talk, and I'm going to be talking about how we can use the periodic motion of, say, electrons and atoms to make clocks. But I'm also going to talk, because we know that the energy levels in an atom are quantized, we can, say, isolate two states, and we could just label them 0 and 1, and we can make a bit that way. And the interesting part is, of course, that quantum mechanics allows us to make superpositions, and that's why the idea of quantum computing is interesting. So there's a lot of work going on around the world. I'll say, give some credit to other groups, but I'm going to use examples from NIST, where I still have a association, and I'll talk about, and it's using atomic ions to make clocks and qubits. But of course, neutral atoms are very good too. There's a lot of groups working with neutral atoms, and the ideas are pretty much the same, how we make clocks and bits. So one question is, why do we want precise clocks? And historically, it's because for centuries they were used in navigation, and the old method was, say, sailors on the ocean. They would, using a sextant, they would measure the angle between their view of a distant star, say the northern star, and the angle between that and their local level. And by using that angle, for example, for north-south, that is latitude positions, that angle would uniquely determine where they were in terms of north-south position. Because the problem was that, and the idea was the same for east-west navigation, but the problem, or an issue they had to deal with was the Earth was rotating and the angle was changing. So they had to know the time. So I mean, that's an interesting story. There's a nice book I'm highlighting there, but that goes through some of the history of that. But what we're going to talk about is the more modern way that time is transferred, and that's through the satellite systems like the GPS. And the idea there is pretty simple. Let's say if you're on the Earth here and you have a clock that's synchronized with a clock on board a satellite, then the idea, you can determine the distance you are from the satellite. If it gets more complicated than this, but let's say we just have a simple protocol where this clock on the satellite will emit a pulse of radiation on every second tick. And then we can determine the distance that we are from the satellite, because the time that we receive it is of course, is past the time of mission. And so the length is just given by the speed of light times the time it takes for the pulse to travel. And the air, of course, is given by the, the air in this length is given by the speed of light times the air and the time. And these days our clocks are, there's different levels of performance, but they're pretty close to the nanosecond level. And so if we can get down to a clock synchronization of nanosecond, that would give an uncertainty in this distance of about 30 centimeters. And just another thing to relate this to is this would be, say, 1 nanosecond. And if we had to maintain that nanosecond in timing for a day, that's about a part in 10 to the 14th timing precision. And it turns out this is about the same as the required frequent precision, the clock tick rate that we have to hold per day to reach this level of precision in navigation. And of course, the real system is 3-dimensional, or actually there's more than 4 satellites, but this gives the idea that if you have if clocks on board satellites are known, and if they know their positions, then we can not only get the 3-dimensional position, but we can also get time, because the system is, in fact, there's more satellites in this, so the satellites are synchronized, and the system is fairly redundant, so we can this protocol works pretty well as long as our clock is running correctly. So what about clocks? And I think the basic idea is, we have, at least as most physicists like myself, and there's nothing sophisticated. We make clocks the way they've always been made. That is, we have some periodic event generator and then a counter, and that allows us to generate time. And of course, the traditional periodic event generators were, first of all, the rotation of the Earth. And another example is pendulum clocks. Actually, pendulum clocks are, they were extremely good up until about 100 years ago, but then things like quartz crystal clocks came along and that supplanted them. But the pendulum clocks actually could be quite good. And so anyway, and today the quartz crystal clocks are very good, but we can do much better, it turns out, with atoms. Oops. So the picture we want to have is, there's 2 pictures. One is, you can think about, say, for an electric dipole transition, that the electron cloud is oscillating. Of course, it's not a simple orbit like this classical picture, but we still have the wave function's kind of fuzzed out here. But nevertheless, there's an oscillating electric charge dipole, that basically acts as a pendulum, like a pendulum clock. And so, for example, some of the early clocks were based on masers or lasers. Now, I think everybody knows what a laser is: light amplification by stimulated emission of radiation. And the maser is exactly the same idea. M just stands for microwave rather than the L standing for light. So, but the idea is essentially the same. So in a maser or laser, we have a collection of atoms, and the atoms are emitting. If they start in an excited state, then they'll emit radiation, and the frequency of that radiation is given by the upper state energy minus the lower state energy divided by Planck's constant. And so this is what provides the standard. And of course, in a little bit more detail is that the oscillating electron emits radiation, and we can win by putting a cavity around the atoms that builds the radiation up and allows the emission to proceed more strongly. And then we sample a little bit of the radiation coming out to generate time. So that's the basic idea here. It turns out or I should say that actually the first ideas or first experiments, demonstrating the laser or maser principle, they were actually microwaves, and actually, but the idea is exactly, it's the same property. It's just a different frequency that we tend to think about here, and I'll say a little bit more about that in a minute. So in fact, this was, so a little bit of personal history. I went to graduate school at Harvard, and I went there in 1965, and this is a picture of the group I was in a little, after I got there. And so the group leader, Norman Ramsey, he's actually one of the most famous atomic physicists of the 20th century. And he and his colleague, Dan Klettner, they had invented a maser, the hydrogen maser, based on the natural oscillations in hydrogen. And actually, one thing to say is in hydrogen, the energy difference that we base this frequency emission on is it's where the outer electron spin is either parallel or anti-parallel to the nuclear spin, that so-called hyperfine structure. And that's what gives these two different orientations of the electron relative to the nuclear spin is what gives the energy difference that we base this emission frequency on. So anyway, this was his group at that time, and there's a picture of me here when I started out. And so anyway, Norman Ramsey, he wanted to have a precise measurement of all three isotopes of hydrogen, and so my thesis was basically to make a maser based on deuterium, and it had some different technical difficulties, or rather differences between the hydrogen maser. The main thing was it was a lower frequency, and so the wavelength was fairly long, about a meter, and so the cavity was pretty big. Anyway, but the ideas were just the same. And anyway, so this was the result of my thesis, the hyperfine frequency of deuterium. And it turns out hydrogen just has some technical advantage, what makes it better. And so the deuterium maser really never got used, but it was about as precise as the hydrogen maser. Anyway, even though this wasn't a startling result, but it certainly told me about how to control environmental effects, and also we were dealing with rather long-lived superpositions. As the atom would radiate, they'd be in a superposition state, and they'd last for about 1 second. And this is important when I talk about quantum computing. So anyway, actually, one thing I want to say though is that the coupling between the atoms and the cavity, they're basically two oscillators, coupled oscillators. And one of the silly technical problems is if the cavity isn't tuned exactly to the emission frequency of the atoms, the cavity, there are two coupled oscillators, so the cavity can pull the frequency of the atomic emission. And so there are ways around it, but at some point it became a problem. So the more common way we think about making clocks now is we have, say, we start the atoms in the ground state. I'll label them 1 and 2 here. Excuse me. And so we initialize the atoms in the lower state, and then we apply radiation for a certain amount of time. That's tuned near the emission, the resonance frequency of the transition. And the basic idea then is we measure the probability of excitation into the upper level, and when the excitation probability is maximum, then we know that the frequency of our radiation source is equal to the natural frequency of the atoms. And then when that condition is met, we just count cycles of the radiation source. So why atoms versus other kinds of clocks? And I'm going to compare to the pendulum clock, and some of the same consideration for pendulum clocks that I'll talk about also come in for things like quartz crystal clocks. Anyway, the frequency is given for small amplitudes is just given by this expression here, where g is acceleration of gravity and L is the length of the pendulum, and so that generates this oscillation frequency. So one thing we have to worry about, are environmental effects. And in this example of the pendulum clock, let's say, oops, pardon me, sorry. Let's say if the length of the arm that supports the pendulum, if it let's say most materials will expand as the temperature increases. So if the temperature coefficient is given by this alpha here, then the change in the length of the pendulum is given by the length of the pendulum times this expansion coefficient times the change in temperature, excuse me. And so even for a very low expansion material, that most metals are several hundred times larger than this example of expansion coefficient I'm choosing here. But certain glasses, for example, can have very low expansion coefficients. Anyway, if I choose this value for the expansion coefficient, then the frequency uncertainty due to temperature changes is about, turns out, almost a part in 10 to the 8th per degree C. So for atoms, this is maybe a simplified picture, but actually some of the first atomic clocks were based on atoms that were stored in glass cells. And in the case of hydrogen, it was a glass cell inside this cavity, and the inside of the cell this glass cell was coated with Teflon. And the reason for that was that the atoms wouldn't stick on the glass that way, and so their frequency would be perturbed very little. They bounced on the walls, but that didn't cause too much of a problem. But anyway, so what about the temperature sensitivity for atoms? For this case, it's actually a lot more interesting. That we have to worry about temperature changes, and of course, what Einstein told us was that for frames that move relative to us, we observe their time to be slowed down relative to our time, that being stationary in the lab. And anyway, so this is called relativistic time dilation. And I won't go into the details here, of course, but just give you an example of some numbers here. So we can calculate the fractional frequency shift versus temperature, which is the temperature is proportional to the average value of V squared for the atoms moving around. Anyway, we get this number here. And so an example is, say, for cesium atoms, they're fairly heavy, which is nice, but it gives about a frequency shift of about a part in 10 to the 15 per degree C versus almost a part in 10 to the 8 per degree C. So that's one of the advantages of using atoms. The other thing too is kind of obvious that any sort of mechanical device, the reproducibility of the frequency depends on manufacturing tolerances. Say the length of the pendulum might not be exactly the same for all slots, and of course it depends on the local value of gravity, and so that's a limitation. The other thing is atom, in the pendulum clock, the bearing that supports the pendulum may wear and cause the length to change, and so we'd have to worry about due effects to that. So the nice thing about atoms is that, as far as we know, and I think everybody's pretty comfortable with it, that all atoms of a particular kind are exactly identical. So I've used the example of cesium-133 there. And the other thing is atoms don't wear out as long as we can keep them around. There's nothing that causes them to change. So actually I've used cesium in this example because in the 50s, people were developing atomic clocks based on the hyperfine transition in cesium, just like the hyperfine transition in hydrogen. In that case, they were using atomic beams that the atoms would go down and they would irradiate the atoms. And then when they changed state, they could reach the hyperfine transition frequency. And just to give you an idea the cesium clocks have been worked on almost about a decade. And so in the mid 60s, by international convention, the definition of the second was changed to be based on the the cesium hyperfine frequency. And here's the frequency of the cesium transition. So basically when 9 billion and so many cycles of this oscillation went by, that was defined the second, the unit of time, the second. And this is still, even though we do better these days, this is the way, standards are defined. What I'm going to talk about here is in the last 10 years or so, we've gone to using transitions, not microwave transitions like in cesium hydrogen. We've gone to optical transitions. And so one reason we do that is just that the oscillation frequency, that is the tick rate of the clock, can be much higher. And so that means any time interval, say the second, can be divided into finer and finer intervals. And so that's why we choose optical transitions these days. And this is an example that we started on in 1982 when at NIST in Colorado. And eventually this was the frequency of the transition of Mercury we used. It's a little over 10 to the 15 hertz. And at that time we could measure it to a little better than a part in 10, about a part in 10 to the 15 precision. So are the ideas, is this idea of optical clocks new? And actually, interestingly, not one of the fellows at the NIST labs dug up this, a text written by Lord Kelvin and his colleague Peter Tate, and they attributed this text they wrote, they attributed the idea to Maxwell, but this was their quote from their treatise on this thing, and they say you can read it here, but she said recent discoveries that there are natural standards such as atoms of hydrogen atom or sodium. They were interested in sodium actually, and they're all maybe not infinite numbers, but there's a lot of them in there, like in every physical property. Sorry. So they certainly had the right idea, but they also say and they were actually thinking of the sodium vibrations they were thinking of were actually electrons, so optical transitions. And so they also say that, the time of vibration, the nice thing about an atom like hydrogen or sodium is that they oscillate exactly the same, and the frequency is known to be absolutely independent of the position in the universe, and will probably remain so now. Well, this phrase in red, they can be excused because they didn't know about Einstein's theory of general relativity, and I'll come back to that a little later. So, but nevertheless, they really had the idea, and they were thinking about optical atomic clocks, more than more than 200 years ago almost. And anyway, so what I'm going to talk about is excuse me, I'm going to talk about not neutral atoms, but charged atoms, atomic ions. And so the two people that are credited with making these ion traps, at least useful for clocks and other experiments, were Hans Demotte at the University of Washington and Wolfgang Paul, who was in Bonn University. And so I won't describe this is a very simple form of this trap that's named after Wolfgang Paul. And I won't go through the details. I could tell, convince the students in about 10 minutes that, how the trap works. But all I'm going to say is that to make these work, we apply a combination of static, electric, and oscillating potentials. And it creates a three-dimensional harmonic will at the center of the trap, so which holds the ions. And a simple, without going into the physics, a simple analog in 2 dimensions anyway is like a marble in a bowl. Anyway, but you want to keep in mind it's a three-dimensional harmonic will. I should also mention that actually Hans Demotte and Wolfgang Paul, they shared the prize in, I think it was, I forget now, 1989. They shared the prize with Norman Ramsey for the invention of the traps, and for Ramsey for his method of doing spectroscopy. So anyway, what I'm going to talk about these experiments we did in Boulder, Colorado at NIST, and my colleague there, Jim Berquist, you see his picture here. He really led this experiment. We worked together, but he was in charge of this particular experiment. And so we used mercury ions, and in this case, the It's based on, I won't go, if you don't know the atomic physics notation, it doesn't matter. We can just still label our levels 1 and 2. And this upper level of this optical transition in Mercury has a lifetime of about 1/10 of a second. So this is the transition we're going to use to try to make our clock. And this one here, it's in the ultraviolet, about 282 nanometers. And of course, we had to realize ways to deal with that with the high frequency, but eventually that was done. So anyway, this is how we got started in the business. And the one nice thing about Mercury and some of the other atomic ions I'll talk about was that Mercury had a lifetime of about 10 seconds. So that means that the absorption range, when we shine radiation on this transition, the absorption range is about roughly a couple hertz wide. And so it's 2 hertz wide out of 10 to the 15 hertz, and it gives very precise fractional frequency revolution. And so that's why we wanted to use a very narrow, very long-lived transition, very narrow, to give this narrow absorption range to get good discrimination on the frequency. So how do we detect our ions? And I am going to talk about I'm going to talk about single ions, and the reason for that is it turns out for the case of Mercury, and there's other things that come in too, but for the case of Mercury, if we had 2 ions in the trap, the upper state of the Mercury transition, this D level, it has an electron cloud shape of like a football. And so it's this non-spherical shape of the electron cloud that can interact with the gradients. So if we had 2 ions of 1 ion on the other and cause a frequency shift. And for the typical conditions in our trap, it's about 1 kilohertz, and we're trying to get way below 1 hertz. So that was that's the reason we went to 1 ion in these experiments. Anyway, the idea there is if we have for detection is that again, this is our clock transition, and let's suppose we try to radiate the clock transition, and then we turn that off and then turn on this second radiation here. This excites a transition to an upper state, which has a very short lifetime, just a couple of nanoseconds. And so when we turn on this laser, let's say the clock radiation is not tuned correctly, the atom remains in the ground state. And then when we turn this laser on, we get lots of scattered light. It's a couple 100 million per second. And all we need to do is detect a small number of the scattered photons to tell that the atom was here. Of course, when the atom is in the upper state, then there's no fluorescence or no scattering from this transition. And it turns out, yeah, so that's what I was just saying. So if it goes to the upper state, this transition can no longer be driven. And so there's no scattered light from this second laser that we turn on. So let's see. Part of the problem in having the Zoom is blocking out the upper thing. Well, anyway, you can read it, but I can't right now. Anyway, anyway, just to say, we could actually get this method of just using scattered light off of this transition was very effective. And so, for example, so what I wanted to say is we can tell when the atom is in the lower state, we get lots of scattered photons. When it's in the upper state, there's essentially none. There's some background scattered light, but we can easily tell, when the light, there's so much scattered light that we can tell with 100% efficiency which state the atom is in when we do this projective measurement. And in fact, in principle, we can see single atoms. Now, turns out for Mercury, we can't, because this radiation is in the ultraviolet, and our eyes aren't sensitive to it. But there's actually other ions. Some people, other popular ion people use for these kinds of experiments is singly ionized barium, which has an optical transition. It's in the blue spectrum, and it's interesting. You can actually, just with a small single lens, if you look at one of these traps, you can actually see a single ion, a single atom. So it's pretty amazing, how sensitive this is. Okay, another thing for this, excuse me. I talked about the second transition. We also, it has another use, and what we've been able to use it for in other experiments too is that it can also be used to cool the ions. And the idea there, well, it's not very complicated. And if I do it right, I can do it in just a few sentences. But the idea is, so when this laser is, impinging on the ion, and when it scatters light, it's giving momentum kicks to the ion in the direction of the laser beam. And so that can heat the ion. But there's also the effect that if the atom is going against the laser beam, the Doppler shift will actually shift its frequency up. And so it'll scatter more light when the ion is moving against the laser beam than when it's moving away. And it's this differential scattering and essentially the average force that causes cooling, so that we can actually, this simple form of cooling, so-called Doppler laser cooling, it works, we can get down, in the experiments, our first experiments we did, the apparatus was at room temperature. And so the thermal energy of the ion was also near room temperature. And this simple form of cooling, we could cool the atoms down from about 300 Kelvin, that's room temperature, down to about a millikelvin. So that would suppress the time dilation effect almost by a factor of 1,000,000. So that's one of the reasons, that it was interesting. In fact, all the clocks these days use laser cooling to suppress this shift. And so this was actually our group, just after the time we did these laser cooling experiments. I did these experiments with my colleague, Bob Drollinger. And then not long after that, we were joined by Jim Berquist and Wayne Utano, who was our theoretical expert and computer expert on the experiments. And so we teamed up together to work. Oh, I'm losing my voice, sorry. Teamed up together to work on this clock. Anyway, so I won't go through all the steps we went through, but it took a long time. So basically, we started these experiments in '82, and then about 25 years later, we kind of had finished what we wanted to do in this. But let me just summarize all the things we had to work on. So the trapping, basically that means when we trap an atom or an ion, that means the average velocity goes to 0. And that means also the average Doppler shift goes to 0. So that takes care of the so-called first order Doppler effect. And then the cooling gets rid of the so-called second order Doppler effect, or this time dilation shift. And pardon me, in the later experiments, we actually went to 4 Kelvin vacuum system. And the reason for that was we could basically freeze out all the background gas. So the collisions from background gas would cause the frequency shifts. Also, it's interesting, by going to this low temperature, also we drastically reduce the thermal radiation shift, the so-called black body shift. It's just the thermal radiation in the room. And I was always amused to think, if you calculate the electric fields from thermal radiation that's in the room, it's actually about 10 volts per centimeter. And of course, we don't sense that, but it's actually fairly strong, and it's a shift we would have to worry about with the clocks. The nice thing is, though, this black body here, thermal radiation shift, scales as temperature to the 4th power. So when we went from room temperature down to about 4 Kelvin, we could basically, we didn't have to worry about this shift anymore. Anyway, so after a long time, as I say, we started in 1982, and after. And then in around 2006, we kind of finished. Jim and the guys working with him, they got down to a systematic uncertainty of about a little under a part in 10 to the 17. And the reason, pardon me, boy, the reason this is interesting is that the cesium standards, they had been gradually improving over the years, but basically the best uncertainties with cesium clocks at that time were just a little worse than part 10 to the 15. And so this was a big improvement. And so, I mean, I think this is certainly, I mean, not that we set the world on fire or anything, but I think everybody's moved to it for these optical clocks for the reasons I've described here. So anyway, I've talked a little bit about some of the effects we have to worry about now, and some of the simple ones that are always there is we have to worry about stray electric and magnetic fields. It turns out, I've mentioned thermal radiation, but say for magnetic fields, and we have to worry about, for example, stray static magnetic fields. And what we can do there is we can measure other transitions in our ion, in this case, mercury, that depend on the magnetic field. And then we can get a measure of the magnetic field that way, and then extract that value and plug it into the shift on the clock transition. So that's how we can take care of some, shifted electric and magnetic fields. But and I've talked, the other interesting effects here due to Einstein, I've already talked about the time dilation shift due to atomic motion. There's a second shift, which comes from Einstein's general theory of general relativity. And it's called the gravitational potential redshift. So basically the result, what Einstein told us was that clocks in a gravitational potential will run slower than clocks in a less strong gravitational potential. And it's called a redshift. Again, this comes from astronomy because, as many of you know, I think that, distant galaxies and stars, the light tends to be shifted to the red because they're moving. And so that's why it's called, in this case of the potential redshift, it shifts the frequency down. So we call it a redshift. In fact, it's the redshift from the Earth at sea level is almost a part in 10 to the 9. And so we have to worry about that, particularly when we compare clocks with the accuracies we have now. So for example, I won't go through the derivation, but this gives the fractional change in the frequency due to this gravitational potential redshift. And just just give you an idea. So that it's actually in a human scale, it's not a big effect. It's a effect we have to work on clocks, but to give you an idea how on a human scale, it doesn't really a concern. And so I have a little story here. Suppose you and your twin sibling were separated at birth, and you live at sea level and your twin lives in, say, in Boulder, Colorado, 1.6 kilometers above sea level. It turns out after 80 years, your twin will only be about a millisecond older than you. So it's nothing we have to worry about in ordinary life, but certainly it's something we have to worry about in our accurate clocks. And in fact, one of the difficulties we have when we compare clocks is we may not know if we're comparing over a long distance, say kilometers or longer, we may not know the local value of the gravitational potential well enough to do an accurate comparison. So it's a real issue we have to worry about. So anyway, just for fun, we did some, we had a clock. This was later after the Mercury experiments. This clock was based on aluminum ions, and it had some features. It had about the same frequency as the Mercury transition, but it had some nice features which made it a little easier to work with. One of the nice features it had, I mentioned that the Mercury had a upper state lifetime about 1/10 of a second. The upper state lifetime of this aluminum transition lasted about 20 seconds. So it was the absorption feature was about 200 times more narrow than the Mercury transition. So that's one of the reasons we chose it. Anyway, so this is I show a picture here of we call this of our single aluminum ion Mercury clock. And obviously it doesn't look much like a watch or a clock. But anyway, what you're seeing on the table here is this shiny silver tube is the vacuum system for our ion trap. And then all this other stuff around here is basically optics and lasers to be able to interrogate and cool the ions, for example. So anyway, for this fun little demonstration of the relativistic the redshift, these are the two guys that were carrying the other Daves in the lab besides me. They were carrying out this experiment, and So basically what they did, they made another clock that was as near as they could identical to this clock. It turned out it was it was held in the room just off to the right side of this picture. So anyway, we called this clock here clock number 1, and we have a clock as near identical as we could make it. We call that clock number 2 in the other room. And we measured the ratio of the frequency. Boy, I hope I could laugh. So so we had the second clock, and we measured the ratio of the frequencies. And this, we didn't do a super accurate measurement. We actually get down to 1 digit in this last page, part 10 to the 18. But for this test, we only measured it to a little less than part 10 to the 17. So anyway, but for this simple demonstration, this is one of the guys working on an experiment, James Chow. And what you can see what he's done here is he put jacks underneath this first clock, and he's going to raise it up here a little bit. And he raises it up. It turns out if he raises it about a foot or 33 centimeters, you can actually see the change in frequency of the clock due to the weaker gravitational potential. So this clock in this room ran faster than the other one, and the ratio of frequencies is given by this measurement. Actually, we still had I didn't write the error, and this is about the same as before, but it was, pardon me, a significant effect. Excuse me. So this is, I just want to say in this experiment, there's a lot of other experiments going on different ions. And there's also experiments on neutral atoms. As many of you may have heard of optical lattices. And the idea there, is to trap neutral atoms, and they can be done with optical fields. Actually, the principle of trapping is really not any different than the ion traps. It uses uses electric and magnetic, the electric fields, inhomogeneous electric fields to do the trapping. Anyway, all I want to say here is that I have a lot to say about this, but the numbers here can be very, very precise as well. And actually, I'm writing this reference up here. It's not this reference here. It's not real up to date, but if you want to find out more, this is a good place to start because it talks about all these different clocks. Anyway, so it turns out one of the nice things about these neutral atom experiments is it turns out the measurement imprecision, and this is just due to the statistical noise due to the quantum fluctuations. It scales as 1 over the square root of the number of atoms we have in the transition. So they can use a lot more atoms than we can with our ions so far. And so they can measure these higher precisions, get there much more quickly than we can with our ions. So anyway, we're actually now at a state where the uncertainty of the ion clocks and some of the neutral atom clocks is about a part 10 to the 18. And I mentioned that the cesium clocks are still not much better than a part 10 to the 16. So, you might, the logical thing to ask, well, should we redefine the second? And we certainly have, and the issue is, I would say, this is more probably a political thing, science politics thing than physics. That is, the worry is if let's suppose we define the transition based on aluminum, the second best on that transition. Well, maybe next year there's some neutral atom clock that'll be 10 times better than the aluminum clock. So, we'd be inclined to change the definition. And I think, so, people are being very cautious, about changing the definition. And right now the definition is still the cesium transition, even though the precisions are, more than 100 times more precise than we can get with cesium. So anyway, what about the future? Well, we'll probably, people are thinking about this, but, they're going slowly on this. So it turns out another whole interesting subject, which has, it's related to quantum computing, and I won't have time to talk about this, is that we can make certain states called entangled states, where there's quantum mechanical correlations between the atoms, which are used with the clocks. And it turns out, in that case, if we can demonstrate the ideas. So far, there's no accurate clocks using this idea, but we can demonstrate the basic ideas. And it turns out that the measurement impression, rather than scaling, is 1 over the square root of the number of particles. It scales as 1 over the number of particles. So we get this huge improvement in terms of the measurement precision by using these so-called spin squeeze states, we call them. The other thing is, so what about navigation? Well, we still use our clocks to do navigation. And actually, one interesting thing is people are thinking seriously about now is, for example, earthquakes are usually preceded by strains in relative positions of the earth. So basically, if you have 2 positions that are spread by kilometers, then the height may be moving relative one versus the other. This is a measure. This is an indication of strain, and then so maybe it would help us do earthquake prediction by this method. Of course, and there's also, physicists were always interested in fundamental science. One of the things that we and several of the other labs did is, if you measure transitions in different atoms, they depend on different relative strengths of the basic forces, the electromagnetic strong and weak. And so if we compare 2 clocks based on different atoms, we can put a limit on how much the basic forces are changing relative to each other. So far, we haven't found anything, but theorists will speculate about that. So we do those kinds of experiments. And actually, of course, the big thing in the last few years has been the detection of gravity waves. And people are, there's ways to think about using atomic clocks, which people are thinking about there. And for example, simple ideas that if you have 2 clocks separated by distance and a gravitational wave comes along, then it's going to cause the separation to oscillate. And those, the shifts in the clocks relative to each other could be used in principle to detect gravitational radiation. And of course, a sport with physicists is to try to show Einstein's wrong, but so far he's held up just fine. And in fact, so, people, what would be interesting, we're not going to blame Einstein, but if we did see a difference in his prediction from general relativity, then it probably signals some kind of new physics, and that would be exciting. So, yep. Okay, so now I'm going to shift to atoms as bits. And so I mentioned at the start of the talk, we can use atomic transitions to also store information. And we can make a classical bit of information with our atoms. We'll take 2 states and we can store information in say, a state we'll call a 0 state and another state we'll call a 1. And it turns out we can also make superposition states. And that's where if we drive this transition only part way, it turns out that, in the ideal case, we can make so-called superposition states where the atom is neither a 0 or 1. It's a so-called superposition between the 2 states. And so this superposition idea is going to lead to the strength of quantum computers. So let me say, let me just say a little bit. Oh, wait a minute, this is coming on. Oh yeah, I was going to show here is this superposition idea. To say a bit is in both the 0 and 1 state at the same time, which we infer from this wave function down here. That seems a little strange. And to make this idea of superposition even more strange, we can take our ion in the trap. We can represent it by a marble in a bowl here. And we can cause the ion to oscillate, and it turns out we can make one example of a superposition state we can make is that we can make a state of the ion motion where at a given instant of time the atom is both on, say, the left side of the bowl and the right side of the bowl at the same time. This makes no sense, but this is the kind of world we live in with our atoms and our atomic qubits. Okay, so why is this interesting? And so if we go back to the energy levels of the atom, so the idea of a quantum bit, and using superpositions, that the bit doesn't have to be a 0 or a 1. It can be both a 0 and 1 at the same time in this superposition state. And the reason this is interesting is how memory scales with superposition states. So I showed a simple example here. Suppose we had 3 quantum bits. And for example, a classical register could store, one 3-bit binary number, let's say 101. But in the superposition sense, the quantum register of 3 qubits can store all the numbers from 000 up to 111. That's 2 to the 3 possibilities, 8 possibilities. And of course, what we're going to grab onto is the scaling. The scaling is exponential. So, and kind of a dramatic example of this. Suppose we have 300 quantum bits. The number of states that this could store is around 10 to the 90th, and that's more than all the matter we have in the universe, all the atoms in the universe. So you couldn't make a classical memory. We can actually make this memory, but to do anything useful, that's the challenge now. So that's where we're at now. So the other nice thing about this is, we get this massive memory storage, but we also get advantage of parallel processing. And it turns out when we make these superpositions, these coefficients out front here can all be different. And so if we flip one bit, it'll change all these coefficients at once. So it's some sense that gives the idea that we can do, sort of massive parallel processing. But of course, we have to remember about measurement in quantum mechanics. And of course, with the standard thing we learn in quantum mechanics is if we can make a superposition, say of just a single bit, when we actually measure that state, that qubit, it's either going to be projected into a 0 or 1 state. And it's true also of our quantum memory. If we do a measurement on these separate states, this whole register will be collapsed down into 1 state. And so we have to keep that, certainly have to keep these in mind. And of course, and maybe not everybody in the audience quantum mechanics, but these coefficients out front are, when we square those coefficients, that gives the probabilities that the atom is measured to be in 1 state or the other. On the other, so I just wanted to mention that actually what really got things going in this field, there were ideas about quantum information going back quite far into certainly by the the early 80s, and but what got things going, people getting excited was it was Peter Shor, a computer theorist who's now at MIT. He came up with an algorithm which one of the results was he showed that if you could make this quantum computer, you could efficiently factorize large numbers. And so maybe that, to some people that sounds like an esoteric math problem, but I think many people know that the security of almost all encryption systems we use is derived from the inability to factorize large numbers. And so when Peter Shor's algorithm came out, you can imagine that the intelligence communities were very interested in this. And so it's certainly very true in the US. That's how the government funded a lot of projects, including ours, to try to develop these ideas. And well, anyway, so I cut to the chase right now. We don't have a quantum computer that does efficient factoring yet, but we hope we're on the way to do that and doing other problems, of course, too. So I'm going to say a little bit about gates here. In a classical computer, it turns out we can make a so-called universal quantum computer with just 2 gates. And I show it doesn't have to be these 2, but these 2 would be sufficient to do universal so-called classical computing. And there's an analog in the quantum world, and we need to do something analogous. So we need to be able to do what we call rotations, and we tend to call it that because what we can think about is our bits on the quantum bits being, say, the states of an electron where the spin is pointing up or down, and we can talk about these transformations we do on the bits as just being rotating this electron spin around an axis. And we can also make logic gates, and one that works is the so-called pi phase gate. And if you just look at the states here, it doesn't look like nothing is happening, but there's this minus sign, And when we talk about superpositions, we can use this minus sign in the gate. And what I'm going to try to do is quickly give you an idea how we can make these logic gates. These we can do just by, when we have our single quantum bit or isolate a single quantum bit, we can do these rotations just by driving the transitions part way. Oh, and let me come back to Peter Shor now. So basically what he showed was that I showed the example for the numbers, but the way his algorithm worked is that basically you plug in all numbers up to the number you're trying to factorize, and then you apply a series of these 2-qubit gates and rotations, we call them, just a series to these bits, and they can be just between two of the bits at a time. And anyway, that's the way his algorithm was shown theoretically. And then one thing I like to think about is that what happens is these amplitudes from all these states interfere. And what I like to think of it it's kind of like the simple 2-slit interference experiments. Here's an example with water waves where the water waves are coming up, hitting this barrier that has some slits in it. And you can see some of the waves go through and they interfere. You can see the destructive and constructive interference. And in some sense, that's what this Peter Shor's algorithm, it interferes the coefficients of these various states to give the answer. And in fact, there's a lot of detail here. I mean, people teach classes on this, so you can't get it at once. But the basic idea is that his algorithm is such that after all these operations are done, you still have a large number of states, but when you project it, the register into one state, it turns out you can use classical number theory to derive the factors in this digit. As I say, I can't convince you that this takes a long explanation. Anyway, but to give you an idea where we're at, to factorize 150 digit decimal number, which is, the cryptographers want to deal with digits larger than that. It takes about 10 to the 9 operations. And just to give you an idea now, we're sort of at the stage now where we could do we're approaching maybe 1,000 operations before errors come in. And so we have a long way to go to make a factorizing machine. Anyway, what I want to give is just a picture of how we might be able to do with science. And so these ideas come from 2 well-known atomic theorists, Ignatius Rek and Peter Zoller. This is our trap. It doesn't look like the first one I showed you, but this one, it shows this 4-rod structure. And the reason we choose this one is become apparent. But basically, the idea is we can store a line of ions in this trap. And their idea, very simply, is if I can do it right, very simply is each of the ion internal states will act as what we call it a spin qubit here, in analogy with electron spin. But we also have to worry about the motional modes of this array. You can think of this as like a 5-atom molecule. And so it's going to have 3 times 5 normal modes of this of vibration. And we're going to isolate one of those modes, and we're going to make a qubit out of one of those motional modes. The simplest one to think about is where the ions are the spacing is preserved, but they're oscillating back and forth in this potential here. So anyway, so we're going to isolate one of those modes, and we can make a qubit if we can isolate the ground and first excited state of this motional mode. And maybe not everybody knows, but these approximate harmonic oscillators, and harmonic oscillators basically have an equally spaced array of states. But anyway, what we're going to focus on is the ground state and the first excited state. And I mentioned we can do I mentioned Doppler laser cooling, and it's a bit more complicated, but we now later had ways to where we could actually cool the motion of these modes down to the various lowest energy state. So essentially we could cool for one of these modes, we could put the motional qubit made by the 0 and 1 state of motion of this mode into the ground state. So anyway, so their scheme just very, high level views. They start, the idea is to start the motion in the ground state so that all the motion is frozen out. And then it turns out, say for this qubit here, we can do a mapping operation where we can map this state of the internal state of this qubit into the superposition of the ground and first excited state of this motion. And then the second part of their scheme is, so then it turns out that, say if we're thinking about the state of motion where all ions are moving back and forth together, then basically when we put this qubit state into the motion, all the ions feel that motion. And so if we can somehow make a logic gate between the internal state of this qubit and the motional state that this qubit shares, then we basically done a logic gate between the first bit and the final bit through this mapping procedure. So that was the basic thing. And in fact, we can do this kind of thing that just to give you an idea. So the first idea is how can we do, so what I'm showing here is just one of the bits in this collection. And we'll assume it's done on optical transition here. The motional states for the experiments we did, the energy levels were separated by about 10 megahertz. And so we could easily isolate these different levels. So anyway, so the first step in their scheme was to map the internal state of this qubit shown by this superposition onto the motional state superposition. And the way we do that is we can actually drive with an inhomogeneous laser field. We can transfer the amplitude of this state up here down into this lower state. And so effectively, we've mapped the internal state superposition into the motional state through this mapping procedure. And then because the second the second bit we've isolated, it's going to feel the motion too. So the general state for this second ion is it's got the superposition of the motion states, and it also will have superpositions of the internal state of the ion. Anyway, what we can do, again, using the inhomogeneous fields from a laser, it turns out we can do a transition where we basically can map the I think I have a video on that. Let me see if I can. Sorry. Oh no. Okay. Sorry. So anyway, where we can say the amplitude of this state up here, it turns out we can go through an auxiliary transition. We go down to this level, and then we basically just keep that laser on and put it back up there. And it turns out when we do this state, it looks like we're doing nothing, but it turns out when you rotate a spin 1/2 particle by 180 degrees, which basically this is mimicking, we pick up a minus sign. And it turns out then that the final, when we do this operation, the final state of this transition is like this. Whoops, and this, pardon me. I showed that logic gate where we showed the minus sign, and this is basically this is the logic gate between in this case the motional qubit and the internal state qubit of this, but it's basically this so-called phase gate that I showed earlier, and it turns out then we can apply different versions of this gate to different ions and carry out the operations that Peter Shor told us about. Sorry about jumping around here. So anyway, and this was we we were able to do this experiment. This experiment I described this here in 1995. It sort of got us going, and it was just about the time when Peter Shor's algorithm came out. So we were lucky we were well funded after that for a while. So Anyway, so what about a large processor? We, 5 qubits isn't going to get us very far. And so the way to deal, one thing we have to worry about is if we stick too many ions in, we can stick, hundreds of ions in one of these single traps that I showed. But the problem is it's become very hard to control the motional modes. And so one way we can get around that is to, use an array of traps. And we'll do the logic operations, say one trap where we have, our 2 logic ions, and to keep ions cold, this is a detail, but we'll use another ion to freeze the motion out to start the logic operations. Anyway, the idea here is that we'll use a fairly small number of ions, so we don't have to worry about all the modes in this combined state. And then the way we move information around is, in this scheme, is that we would just literally move the information bits around. And this kind of schematic diagram, the way we do that is we put just different electric potentials on these control electrodes, which grab onto the charge of the ions, and then they can be, moved around. And actually because we're moving them around, and because they can be, the ions can heat up due to thermal radiation, we actually need a second kind of ion to put into these experiments. And this one, it has different energy structure than our qubit ions. And so we can shine a laser beam on it to do the laser cooling. And because the ions are coupled by the Coulomb interaction, we can cool the logic ions down to these low energies, and also do the measurements on them. So anyway, this is a first try. This is quite a while back. And this trap, it doesn't look at all like the traps I showed, but in fact, it's a 2D electrode surface, and the ions. So I can't describe, but basically that each one of these little squares here, it acts like one of the traps I showed in the previous view graph. So we can sort of one or a few ions in each one of these traps, and then to move the ions around, we could apply electric charges to these separate electrodes. And we kind of did a basic demonstration of this idea, but all this has to be perfected now. So there's still a lot of work to do this. But anyway, this is the kind of way we envisage, or one way we can envisage doing, building up the scheme to do algorithms like Shor's algorithm. And I should say, first of all, there's a lot of other labs doing just ions. In fact, there are almost 100 labs doing ions that are maybe not trying to build quantum computers, but they're doing things relative to or relevant to quantum information. So there's a lot of labs doing ions around the world. And this last is probably, it is out of date by now, but this list lists some of the labs around the world that are working on just ions to do this quantum computing. And of course, there's many other platforms. I mentioned people are, doing similar things with neutral atoms, but there's Josephson junctions, superconducting junctions, so-called quantum dots, and NV centers, and single photons. And there's just a whole number of platforms people are trying to work on. One of the more popular one is to use Josephson junction qubits, and so there's a lot of emphasis on those. And anyway, if I won't swear that this is still up, but this website here had kind of kept track of all these different groups, what was going on. So anyway, what's of course the important parts of the experiments are shown here, and this is our group in the not in 2018. Yeah, so you saw the 4 people that we started with, and it fluctuated around 30 for quite a while, and this is what the group was in 2018. And certainly, it wasn't us 4 guys that I showed before. These are the people who are really doing the experiments. So it was really a big team, and we had several different apparatuses. And these experiments, it always helped to have at least 2 or 3 people running experiment. It's possible to do it with one person, but it was much easier with 2 or 3 people. So we had a number of experiments doing on this. And we also had some, we had support NIST. We got support from NIST, internal support, but we also had, funding from other agencies that were interested in these ideas. And so, anyway, it's a big operation. And another thing I want to say is, at NIST we were very lucky because we had really good managers, and so most of this work that was done. It was done when Catherine Gebbe was our laboratory director, and she passed away a few years ago. But anyway, and it's now taken over by Carl Williams. But anyway, what I wanted to say here is that the management was very supportive, and they didn't try to manage us. So they basically, we couldn't do crazy things, but basically we could choose the direction we wanted to go to try to realize the experiment. So it's really a great environment there at NIST. And that's it. So thanks for listening. And
thank you so much, Professor Wineland. And really, we are talking about the quantum computers these days, but actually that is on top of many decades of atomic physics research in NIST and many other places, and really the quantum information is just a small part of this big business. Okay, yeah. Thank you so much.
Yeah, and, I should have mentioned that actually what I think most of us, I mentioned the Peter Shor's algorithm for factoring, and I think what most physicists, certainly myself and other people, I think where the real use is to be able to simulate other quantum systems that you can't simulate accurately on a classical digital computer. So I think that's a hope of many of us, that we could do many interesting problems, not just factoring. We could do a lot of physical problems, and so that's one of the hopes.
Yes, quantum many-bodied problems is
sure.
Yeah. Thank you so much. And okay, thank you so much for your nice talk, inspiring talk, and I would like to invite you physically to Korea sometime. Okay, thank you so much.
Yeah, you're welcome. And thanks for the invitation. Yeah.
Okay, this wraps up the Professor David Wineland's plenary talk for the 2022 KPS Spring Meeting. Thank you.